We see this object rotating, going through centripetal motion at a regular frequency, a regular period, which means it's going at a regular angular velocity. And what I want to be able to do is to use this in order to figure out how I can create a function of position and time when it comes to an oscillating object. An object going through simple harmonic motion, just like a mass on a spring. I know I can find a way. I know I can. Our most powerful equations were when we could relate our position to a time. Those are our most powerful equations, and I will do the same. I will be able to do the same for an object that's oscillating, even if the acceleration is whack, even if the velocity is whack, and these things are constantly changing. We now finally get to understand how to do this. So, if we have this object right here that is spinning around, if I change my point of view, it looks like it's going at it from the side. That is going to be my key. Now, if I'm going to be honest, in this point, we have a constant speed, so it's not quite the same. But our angular velocity and our period and our frequency are staying the same, just like they are in our other problems as well. We saw that when we have a mass on a spring, no matter what happens, we are going to have the same period if this object just goes up and down forever and ever. It's going to have the same period. It's going to have the same frequency. It's going to have the same angular velocity because of that. So what do? If we take a look at this from the side, right? Then we see this object going side to side, just like a mass on a spring. If we see this from up above, we see it going into a circle. And what we can see is that this sideways motion, we are able to connect this X position to this circular position. Okay, so let's go ahead and freeze it right there. Okay, well, we're going to freeze it right there. We're going to pretend that this is right at the 0 degrees mark. And I'm just going to start it right there. We're saying that this is 0 degrees. Okay, we have rotated 0 degrees from here. And if what that looks like over here, when we look at it from the side, it looks like this. Okay, looks just like this. 0 degrees. And we can also refer to this as 0 degrees. This is the same object, right? So this is 0 degrees. Now, if I go if I go rotate to the other side, it's not bad. If I go and rotate it to the other side, we have made how much of a rotation? How many degrees have we gone through in that time period? Its new position is going to be pi. And what that would look like from over here is, if we look at it from the sideways view, we have gone from the right side over to the left side. Right? We have now come over here, and we are also at a rotation of pi. That's what it looks like from the side. And what that is we have gone from one of our extrema to the other. We've gone from one extreme to the other, and that was pi. If we go all the way back around, right, from our point of view, that's what it looks like when we have gone a full rotation of 2 pi. What we're doing is we are equating one of these cycles in my periodic motion to a revolution in circular motion. One cycle is the same thing as a revolution. Okay? And so what I can do with this is I can predict right now, I can predict what my X position is going to be. At this point, we have a certain radius. We're going to call this a radius of R, and we have a radius of R here. Or really, let's not call this a radius because it's attached right here. Let's go ahead and call this is the maximum that we said. This is the maximum displacement that we're going to see with this object. We have a name for this. If we see the maximum displacement on a sinusoidal graph, we see the word and we would refer to it as A. A for the amplitude. So we're going to say that this amplitude is the same thing as when we look at this from a circular point of view, the radius. Okay? If we want to find the X position of this object, what we can do is we can say, hey, you know what? Go ahead and take whatever my angle is, or the X position, take my radius, and we're going to multiply it by the cosine of whatever my angle is. In this case, my angle is pi. If I do that, X is going to be equal to R times the cosine of pi is -1. So X is going to be equal to -R. Or in this case, let's take this over here. Do the same thing, but we'll put A instead. A cosine of pi. My angle is A times -1. X is equal to -A. And that means that it's just A to the left. What if we do this? What if we take this and let this go all the way around? And I view it from above, it looks like this object is just going straight up and down, right? And I'm trying to find my X position again, right? So my X position for this, the cosine of pi over 2, right? Because that's the current position based off of the 0, 90 degrees, is going to be equal to 0. Because the X coordinate, if I were to make an XY plane, my X coordinate is going to be 0 because it is on the Y axis. If I were to look at this from the side point of view, boom, we see that as like hiding behind the pole, or honestly, it's at our theoretical equilibrium, right? So if we have this, X is equal to A times the cosine of pi over 2, our X position is equal to 0. That is when we take our amplitude, call it meters for now. When we take our amplitude, that is the maximum displacement. That is my extreme. It's another way of saying maximum, another way of saying extrema. My amplitude is the farthest it can go, and I am using cosine as to see what portion of the way am I to my amplitude. Now, that's nice if we have an angle. But we're taking a look at this. A lot of times we don't have an angle that we're dealing with, right? A lot of times, though, what we do know is we know the time of how long it took. This came up. We were not given an angle. Angle is just a mathematical tool that we're using to kind of show how far into this we are if we were comparing this to circular motion. But I'm given times usually. So I need to put this in terms of time. So what I'm going to do instead is, we know that if an object is rotating around, it is going to be rotating at a certain speed, omega, an angular velocity. And so how long it takes to get over to this position from 0, right? If I have this object at a position of theta and it started at 0, well, we know that omega is equal to delta theta over delta t. If we start from 0 on both ends, that means omega is equal to theta over t. So if I want to express the angle that is in here, if I want to express my angle theta, oh, that's a horrible theta. Oh my goodness. If I want to express that, I can change this from x equals a cosine theta. I can change this to x is equal to a cosine omega times time. Now, for a mass on a spring, this will get you most places. However, if we take a look at our formula sheet, we see something. We can see that this is actually seen as 2 pi f. What we see on our formula sheet is equal to this. X is equal to a cosine theta 2 pi times the frequency times time. This right here, this frequency is going to be referred to as cyclic frequency. Ugh. The cyclic frequency of this object. And the reason why we know that is because omega is equal to 2 pi f. And what's also interesting is that means the angular frequency, f. F reminds me of t, because f is equal to 1 over t. If we take the period of a mass on a spring, that means that we have t is equal to 2 pi m over k. If we know that omega is equal to, oh man, I always forget this. It's equal to 2 pi over t, or it's equal to 2 pi times f. That's actually, let's use that. It's equal to 2 pi times f. Then that means that omega is equal to 2 pi times, or divided by, 1 over the period. 1 over 2 pi k over m. This is something that is on our equation sheet that I gave you, your vocab sheet. Okay, that cancels out. That means omega, the angular velocity of this object, is simply just equal to the spring constant over the mass on the spring, and having a little square root on there. Wow. Okay, so the angular velocity for a mass on a spring is equal to root k over m. And this can also tie into, this is the same omega that is found in here. So that means for a mass on a spring, this isn't on your formula sheet. That means that this omega can get turned into a cosine. That's freaky. But that's not on your formula sheet. What if we're talking about a pendulum? What if we're talking about a pendulum? The same thing applies. With a pendulum, we're not really worried about x, because on a pendulum, we are thinking a pendulum moves in angles. It already has angular position that is given to it, right? So we're not thinking about this in terms of x. That was just specifically, let's see, I'm going down to this little simulation. Yeah, you remember this one, right? This already happens in terms of angles. So we're not really worried about a function that translates an angle to an x position, because the angle is really more of the important portion of this anyway. Okay, so we're not really worried about the equation. This equation is mostly relevant for a mass on a spring. So we could say that this is the position of a mass on a spring, and this is the spelled out version. This is the one that is actually on your formula sheet. With that being said, what if, though, we want to find the angular velocity of our pendulum system? Well, what we do is we have t is equal to 2 pi root L over G. We know that F is equal to 1 over 2 pi root G over L. Then we know that if we just multiply this by 2 pi, omega is equal to 2 pi times F, which means that omega is equal to 2 pi over 2 pi. There are lots of fun little similarities in physics. I'm glad I get to introduce you to this one. I'm glad that you're present with me at this moment in time. The omega of a pendulum is equal to this. All right, that's enough for this video. I'm going to give you some example problems in the next one. How long did this take? 17 minutes. Oh, Lord, that might be the longest one yet, but it was important. I'm glad that we could see how we get this equation derived. I'll see you in the next one. Busters!